So in this video, we're going to have a look at differentiation from first principles. And as the name might suggest, what we're doing here is we're going back to the start of the story of calculus. So what we really want to start thinking about is, what information do we hope to gather by differentiation? What is it about a function or a graph that we will know by differentiating? And the words that might spring to mind are things like the rate of change, or even gradients. So there are two words that you might associate with this idea of differentiation. So another thing that we want to start with, I feel, is a nice graph. So on our set of axes, we may have some function, and it might be a curve, and we could represent that as being f of x, or even y equals f of x to represent what that curve has as a rule. And what we really want to know is how this function changes as x changes. So we want to think about the rate of change, we want to think about gradients, and we know things about those. So what we do when we differentiate from first principles is we consider a point on the curve that might be at what we're going to call x. So this point here is the point we're interested in, and it must have some y value over here that's represented by f of x. And what we want to do is we want to draw a tangent line to that curve, so it just touches there, and we want to calculate its gradient. And that gradient would represent the rate of change at that point. But here we run into a problem. If we are only considering one point on the graph, our gradient formula that we know from the past, which you might remember as being the gradient is equal to y2 subtract y1 over x2 subtract x1, it relies on having 2 points. So what we're going to do is we're going to go to another point on this graph, and we're going to calculate the gradient of a secant line that joins those 2 points. And this point's going to be represented by the x value of x plus h, which means that this distance between here and here must be h. And if we have f of x plus h, that represents the y value here. So if we put x plus h into the rule, that gives us a y value, and that y value in particular would be here at f of x plus h. So now we have a run, and we've also got a rise here. So this rise, if I just draw it out to the side over here, the distance here would be equal to f of x plus h minus the function evaluated at x. So if we have a gradient formula that used to do the difference between two y values divided by the difference in two x values, we can now use this setup that looks a little bit more complicated, and granted it is a little bit more complicated, to actually think about what the derivative function is going to be. So we're going to think about this as being f of x plus h minus f of x, which is the rise over here, and we divide that by the run, or the difference in the x values, and we discussed before the difference between x and x plus h is simply h units, so we can drop that in here. So what we're going to do now is we're going to think about, we could make this secant look more and more like a tangent line if that h value got smaller. So a way of representing that in mathematics is to let h approach 0. So we're going to use a limit here, and we're going to have the limit as h approaches 0. And the reason why we don't just put in there that h equals 0 is we can't divide by 0. So this idea of a limit is kind of a nifty way of getting around doing some maths that you can't really divide by 0, but we can almost divide by 0. We can let h get really small, or we can let it approach 0, which is what this is representing. And then symbolically, what we've calculated is the derivative, which we represent as f dashed of x. So we can say that f dashed of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. So let's do a particular example now. And our example is going to be that if f of x is the function x squared plus 4x, find the derivative f dashed of x. And we're going to use this formula here, which is the definition by first principles, to calculate that derivative. So we're going to start out by saying that f dashed of x must equal the limit as h approaches 0 for f of x plus h first. So what this means is wherever there's an x in our original rule, we're going to replace it with x plus h. So this is going to become x plus h all squared, so that's x squared when we put x plus h in, plus, and then we're going to have 4x plus h, because wherever there's an x in our function, we're replacing it with x plus h at this stage. And then we subtract away, and here it's really, really important to use a set of brackets, because we're subtracting away f of x, which has two terms in it. It's got x squared and plus 4x. So we're going to put here x squared plus 4x. And then the other part of the formula is, if that's the rise, then we have to divide by the run, which is h. So next up, we've just got an algebraic problem to work through. So this derivative, f dashed of x, is going to equal the limit, and I'm going to leave this in my working as h approaches 0. And now we're just going to simplify out this problem. So x plus h all squared is actually equal to x squared plus 2xh plus h squared. And then we have plus 4x plus 4h when we expand that out. And then we're also going to have minus x squared minus 4x. And then, of course, all of that is going to be divided by h. So now what we'll find is there's some terms that will cancel on the top line of this fraction. So here we have an x squared, and I'm going to cancel that with negative x squared over here. Likewise, I have a plus 4x here, and I've also got a minus 4x here. So we can cancel the negative 4x with the positive 4x. So all that's left is 2xh plus h squared plus 4h, and we notice that now h is a common factor in all of that. So in this next line, I'm going to factorize that out. So our derivative is going to equal the limit as h approaches 0, and 2xh, once I've taken the h out, is just going to be 2x, and then plus h squared when we've removed h as a common factor is just plus h, and then the 4h here would just leave behind 4 when factorized, and we're going to divide all of that by h still. And this reveals something else that we can cancel, as we've got a h as a factor in the numerator and the denominator. So we can cancel that with that. So really what we've got is the limit as h approaches 0 of 2x plus h plus 4. And now that we don't divide by h, we can evaluate this limit by just letting this h equal 0. So if I evaluate this limit, this term is going to approach 0. So checking what's left behind, we're going to have a 2x and a plus 4 that's not affected by h approaching 0. So therefore we find that the derivative f dashed of x is simply equal to 2x plus 4. So that is the answer to this question if we differentiate using first principles.